And so that the equivalent resistance is this, because I want to get the form E is equal to I times the equivalent resistance. I want to make it into one resistor. So the equivalent resistor of this circuit is simply the source EMF with its R equivalent, one resistor, which is R1 plus R2. In other words, they just add up numerically. That's the easy case. The harder case is when they're in parallel. If you have a resistor like this and a resistor like this, R1 and R2, could be many. That case, well, here I derived that for the series. In parallel, here the thing is, the key idea is in parallel that V is the same across all. Because these are wires and they're equal potential. So whatever potential is here is the same on this end of this resistor and this end of this resistor, like that. So if you have the law, V equals IR, and we're trying to find the equivalent resistor, which is V over I. Now to do this simply, because the V is the same on both, and we're going to be trying to adding things, the thing to do is to make the V in the denominator. So I would rewrite this as 1 over R is I over V, right? And then let's see. So what is I? I is equal to I1. See, because I have I coming in, the total I is split into two parts, I1 and I2. So I have I1 plus I2. Now what is I1? Well, I1, there's a voltage across I1, which is V, the same V, divided by R1. And likewise with I2 here, I have a current through I2. That same voltage is across I2. And so I get that. So I just put those in here, I1 being V over R1, and this is V over R2, and all of that is divided by V. So what you can see, the arithmetic is just that I cancel out the V's, and I get that the 1R that represents those two in parallel is 1 over R1 plus 1 over R2, and I cancel out the V's. So this is the formula for resistors in parallel. And I think I show you in the next slide. Here's that same derivation. And here's a quicker way to do it. I personally don't like to work with reciprocals because you have to stand on your head to get them right. You know, it's 1 over R and this sort of thing. You can do a little bit of arithmetic on this, a little bit of arithmetic. Namely, multiply this and just do something like this, R1, R2, put an R2 up here, plus make this the same denominator, R1, R2, and put an R1 up here, okay? And that's equal to 1 over the equivalent resistor, okay? So now they have the same denominator, so I can draw this like this, put it over the same denominators, and okay, let me do it in easy steps. 1 over RE equals R2 plus R1, because these are the same denominator, I can simply add them, R1, R2, but now I can flip the whole thing over, and I get the R equivalent is equal to R1, R2 over R2 plus R1. So I find this a little bit easier to work with myself, and in fact you can generalize it to any number of resistors in parallel. I have it here with a quick way to do it. You just take the product of all the resistors, R1, R2, R3, R4, blah, blah, on top, and underneath you take them in sets one less than all you have. So if you have 3, you take product of 2, like R1, R2, R2, R3, R1, R3. And if you do that, you get the thing without standing on your head. So that's just a math trick I happen to like. Like, for example, if I'm going to do this demo over here, let's see. Recall this thing here. This is the voltage. If I can get the thing here. Yeah, this is the voltage across something. I always measure across things. Here is my voltage source, this 12-volt battery. I'll turn it on. Okay, now here's a current meter. Current meter, which is in the line. In other words, I want to measure the current. I have to make it go through this meter. It's like there's water flowing in the pipe. I have to put something in the pipe to get the flow across through it. So this is an ammeter. Oh, what am I doing here? I must be electrical. Anyhow, so now this measures the voltage across something. For example, across this battery, plus to minus. Oh, we're getting our usual 13 volts thereabouts. And that's the voltage across the whole circuit. It should be, as we said, divided up across these two resistors. Now this one is 3,000 ohms. This is 1,000. So this is a bigger resistance. It's going to suck more energy out of the 13 volts. In fact, it should be in a ratio of 1 to 3. So this one should be, oh, that's around 10. So we're missing 3. This one should be about 3. Pretty good. Okay, so you see the 12 volts, 9 of it was used up here, and 3 were used up here, roughly. I guess, what was it, 9? 10, okay, 10 is better. Okay, so now let's do something where I'm going to, I did this before, add a resistor in parallel here. And by now, I can't fool you, will the current, total current here go up or down? Oh, let's do the calculation, by the way. I have 13 volts, and I had 3,000 plus 1,000 in series makes 4,000. So I have 4,000 into 12 volts. Should be about 3 amps, or 3 milliamps, which is about right. You see that? This is in series now. And I take my total voltage of 12, divide by 4,000, I get about 3. I'm doing this in my head, so you won't get one decimal place out of it. Now, the thing I fooled you at last time was to put another resistor but in parallel. And now I can't fool you. Now you know that I'm giving it another path, so the current should actually go up, because the current can go through here. And it also is seen by this formula. So it goes from 4 milliamps. Oh, what happened here? That isn't much, is it? A little bit. All right, let me give it a very much easier path. Let me get 500 ohms. Now it can really get, instead of going through this 1,000, it can go through 500. It's a much better deal. So now it should make a difference. Yeah, see, it went from 3 to over 4. See, the thing that's really controlling things is this guy. He's 3,000. So he's really a big resistor blocking the way. So the fact that I made it easier here is not so bad because the resistance here is less, but this big resistor here is holding things up. But let's do in our heads, how much resistance are these two together? Now, if you had to do 1 over 500 over 1 over 1,000 in your head, you're a better mathematician than I. But we can do it with that little formula here. Suppose we do the product. A half of 1,000 times 1,000 is like a half. Divide by the sum. 1,000 plus a half 1,000. So if the product is a half and the sum is 1.5, so the resistance here should be 1/3, right? 1/3 of 1,000 ohms, about 300 ohms. That I can do in my head. You follow that? Okay. So, yeah, and right. Okay, so that's about 300 ohms. This is about 3,000. There should be 10 times more voltage across here than here because this is 10 times more resistance. And this one is a tenth as much. So let's just see if that's true. I haven't done this before, but I believe in Mr. Ohm. So, almost 12. And we're saying it should be 10 times less because this is 300 and this is 3,000. So I get almost 12, and I say a tenth. Should be about 1 volt across here. And it should be the same across both. There you go, 1 volt. And the same 1 volt across here. And the same 1 volt across here because this is all connected by wires. Okay? See how we do that? All right. You know, that's really about it. I think I want you to understand. No, oh, yeah, there's just one other great thing that I have to talk about. See, I want to talk about wiring in your house. That may take up the rest of the. Actually, is there any reason why? Well, you're going to do resistors in the lab. Let me postpone this capacitor stuff. I really want you to understand what's going on in the wiring in your house. And well, here's about meters, and here's that thing. Okay, now batteries in series and parallel. Or here's the Kirchhoff law thing, and that is that the sum of the voltages around the loop have to add up to 0. Because you start out someplace, you end up with the same. This raises the potential, this lowers the potential by the same amount. This is like water pumped up and flows down and loses all its energy. So that's the law. And the other law of Kirchhoff is that as much current flows into a circuit element as flows out. So there should be no problem there. I won't bother you with that stuff. Oh, yeah, there's resistivity. Okay. You can read this. It's in the notes. Power is a good thing to know. The voltage drop across an element is IR. That's per coulomb. But if you multiply by the amount of current, that is I times IR, you get the amount per second. Okay, now the two things I wanted you to be able to do at the end of the physics course, I'd be very embarrassed if you take a whole course on electricity and don't know how to jumpstart your car. This would be total embarrassment. So the point is, if you have a dead battery and you have cables and you have a friend who has a live battery, how do you do it? Have any of you had to do it ever in your life yet? I've had to do it a number of times. I carry cables. So in case you have trouble, call me. But the important thing is that what you're trying to do is replace the battery that's in your car that's dead with a battery. Here's your battery, and it has these terminals on it, one of which is negative and actually is attached to the frame of the car, which we will call ground. And there's a positive thing like this. And you have wires coming out of that battery to your car, to the starter, to the key. And the electricity flows out of here and you start your car. Okay, but suppose this is dead. Now, what you really have to know is that you're trying to put a battery, a good battery, in the place of this one. Now, the question is, here's this battery, and it's got plus and minus terminals. Let me even make it ambiguous which way it is. It has plus and minus terminal. Now, how do I put it in? Do I put it in this way or that way? It's very important. If you put it in the wrong way, you'll get smoke and flame, and you regret it. What do you think? Do I put plus to plus, minus to minus, or minus to plus, or plus to minus? Let me say plus to minus? Plus to plus. I like that, yes, because you're just trying to make this guy do what this guy was doing. So you put him in this way, plus this way. So what you'll have like a cable that is red with a clamp on it, and you clamp it here, and the red cable from the red goes to the same type of polarity, and the black one goes from the same type of polarity. In other words, don't get the red going to the plus to minus, because then you'll have it. You'll be putting them in what we call in series. Minus plus. You don't want to do minus plus and connect this to this. Definitely not. Okay. If you do that, you'll, worse than flunking the course, you'll probably never get out of the parking space. At least not right away. So that's known as putting the batteries in parallel. Now, the other thing I wanted to talk about is when you get your electricity bill, what does it mean? You get kilowatt hours. How much kilowatt hours? What is kilowatt hours? Well, power is I squared R, power. And that's the energy per time. And it is in units of watts, which is joules per second. It's the energy per second. That is not what you pay for, you see, because it doesn't matter how fast you use the energy, it's how much you use. So it's not how much you use per time, it's also how much time do you use it, how long do you leave the lights on. If you leave the lights on, you're using power at a certain rate. But how much they really care about is over what time do you use it. So what they charge you for is energy, which is the power that you're using times the time you use it. So the unit is watts times time, often in hours, so watt hour. And in fact, you use so much that it's thousands of watt hours. So the unit that is commonly on the bills is kilowatt hours. That's what they charge you for. Roughly it's about 10 cents a kilowatt hour. So for every kilowatt hour you use, they'll charge you a dime. So on my bill here, do I have it up there yet? No, let me see. I guess it was. Oh, what's going on here? I want to go back here, I think. Yeah. So my bill this time, I got it off cheap, was 263 kilowatt hours. Oh yeah, you see, 263 kilowatt hours. But I used, that's my quantity. If I use less than that, they charge me low. So I only use 129, and they charge me 12 cents a kilowatt hour. So I ended up paying $16.57 for those 129 kilowatt hours. Right? Okay. Now, so what's your, and PG&E actually says we deliver energy. So there at least they were honest. They deliver energy, not power. They call it the power company, but what you pay for is energy. The power times the time you use it is what you actually pay for. Which is right. It depends on the amount of coal they burn and stuff like that. Okay. So let's go on to this. Namely, I showed you a little demonstration of a fuse. So the old-fashioned fuses looked like this. It was just a little piece of wire, and you sort of threaded it into a circuit. It looked a little like this. And when too much current flows through a wire like that, it gets hot and it burns out, like my demonstration did. But here's what goes on. So your power company is represented by this voltage source, EMF. And in your house are wires, two wires, always two wires. Now, right now, there's no current flowing because nothing is attached. The only thing that they have here, well, in addition, somewhere over here, they have a meter which is going to measure how much current you ask for. And also a fuse. If you ask for too much, the fuse will blow because the wiring in your house can only stand a certain amount of current. So the next picture, I hope, says, okay, let me turn on something. And you see, I put an appliance, I say you turn on the lights. What I'm doing is I'm putting a bulb or lamp across these two wires. There is this electromotive force across the wire, and so the current is going to flow through. And now my current meter, if you've ever seen one, I think I have a picture someplace. It's the meter that has like a disc that rotates. Have you ever seen it? Go down in the basement, you see that? Let me see if I have one here. Oh yeah, it looks something like this. There's a kilowatt hour meter. See, it's kilowatts, that's a power times time. And you see this little disc here? If you go down in your basement, if somebody's using electricity, this disc is going around. It's being told how much current is going into the house. And as it turns, it's linked to these dials, which count up how many turns it makes. And that tells you how much power energy is actually being used. Okay, so let me go back. And I just want to show you this thing sort of step by step. If I put one appliance across, it's across the power supply, 120 volts. If I do the next, turn on, say, the TV, I'm putting on something across the same parallel lines. So it sees the same potential difference, 120 volts from the wall, except that now current is flowing through this guy, and this guy, because they're in parallel, the resistances of the whole thing is lower. Two resistors in parallel, lower resistance, so more current flows through the watt meter and through the fuse. And if I keep doing this, I add yet another device, I have three currents now. Now the limit of this is, if something bad happens and a short occurs, then a lot of current is going to try to flow through. At that point, that's called a short circuit, just a wire, so the current can go wow right through here. Remember, like it jumped up off scale? If that current jumps off scale, the wires in the house could catch fire, and you don't want that. So what you want to do then is have a fuse here, which will open and stop all the current in the house. Or a circuit breaker, which will pop open, and then you'll have to go down and reset it. But make sure you found out where the short was, because the short is still there. You put the circuit breaker down, the current is still going to flow, it'll pop again. So this is just a warning to you, something bad is going on, there's a very large current drawn, and you don't want that to happen. Okay? So this is what I want you to know about when you appreciate what's going on in your house. When you turn on the light, you're putting your circuit element across 120 volts, and everything you do will be in this parallel circuit type of arrangement. This is not trivial, you're doing it all the time. Okay, folks, see you Friday.